Welcome to the third section of this course, Avoiding Common Threading Issues. In this section, we will touch on a few performance and multi-threading related topics. We will learn which are the common issues that can happen when dealing with multi-threading, and learn how can we fix them in the code or avoid them altogether with better design. We will also go back to our Twitter client and learn how to make it handle multi-threading and share resources in a safe way, in order to avoid any issues with writing the tweets to the file system. Now, let's proceed with the first video in this section, multi-threaded contention issues, deadlocks and livelocks. In this video, we are going to look at common issues that arise in multi-threading applications, such as deadlocks, livelocks, and thread starvation. As we have mentioned already, there are a few common issues that can come up in a multi-threaded application. All of them have a small set of common reasons, and, with proper design decisions, can be avoided. Most issues in this category have to do with accessing a shared resource in order to change its value. As changing an object's value is also called mutation, these issues can be called mutability issues. Usually, in order to change an object's value, a thread first has to read the object, then, based on the existing value, create a new one and write it back. When multiple threads do this in the same time, they may race against each other, therefore rewriting each other's result. This usually yields to unwanted behavior in applications. Some multi-threading issues are the result of undeterministic execution order. In most multi-threaded situations, we cannot guarantee the order in which different threads run in, and we should assume this order is unknown and can change. Last but not least, Java has an interface called lock. Locks in Java are meant to prevent multiple threads from accessing the same shared resource at the same time, and set up coordination between them. Think of this lock as a token passed between threads. Only the thread having the token can perform certain operations. When we have multiple locks involved between multiple threads, we can easily reach a situation called deadlock. This means the threads are waiting for each other and cannot proceed. This can mean that the application is stuck forever in the current state. As mentioned before, a deadlock is a situation when two or more threads are waiting for the same resource. In this context, a resource can mean anything from a simple integer variable that needs incrementing to a file writer, a database, or a network connection. Usually, developers represent these shared resources by locks in order to coordinate thread access. However, bad design can result in the application getting stuck. A real-life example, which you may find familiar. Imagine two people coming on a narrow corridor from different directions. If they are too polite and keep inviting each other to pass first, this can be described as a deadlock. To create a situation where a deadlock occurs, let's start writing a simple multi-threaded application, where each thread is waiting 1 second, then prints a message to the console. As all threads will be submitted to the executor service at the same time, the messages will be printed in the same time. To recap, in this coding exercise, we have seen how multiple threads can print text in parallel. In the next bit of code, we will build on the previous functionality but introduce a lock. This way, only one thread can execute at a time. This will result in the messages being printed sequentially, with a 1 second break between them. As a summary, in this coding exercise, we have introduced the concept of synchronized objects. Those are objects which multiple threads are taking turns in order to access. In the next example, we want to introduce a loop and have every thread execute inside it. However, since a lock is acquired, only one thread will hold the lock, preventing the other threads from running. You can describe this as a deadlock from the other thread's perspectives. In this coding exercise, we have shown the first issue with multithreading, a single thread holding the entire application from executing. Let's make this a bit more complex and add a second lock. And let's implement two threads which acquire the locks in opposite orders. The first thread will acquire lock 1, then lock 2. The second thread should acquire lock 2, then lock 1. Once both locks are acquired, a message is printed and the program exits. But since no thread can acquire both locks at the same time, and each thread is basically waiting for the other, this is a proper deadlock. The application will wait forever. In this exercise, we have seen what a deadlock is, a situation where two or more threads are blocking each other, not allowing the application to continue execution. The next concept we'll learn is the livelock. This is fairly similar to a deadlock, but usually arises in more complex algorithms, where the threads are retrying the operations, trying to succeed in acquiring both locks. However, while both will go back and forth in trying to get the locks, neither will succeed. This is called a livelock. The threads are not completely frozen, but the application is not moving forward. A real-life example, which again you may find familiar. Imagine two people walking in a corridor towards each other on the same side. They are polite and trying to let the other pass. However, as they are trying to move to the side, they are both moving in the same side, not knowing that the other will do the same. This is the real-life livelock, since both people are trying to fix the situation, but neither is succeeding. To create a situation where a livelock occurs, let's use the previous example with the application having two locks. This time, let's put everything in a loop that will only exit when the thread has completed successfully. The threads will retry acquiring the locks, but not succeeding, resulting in a livelock. When you run the application, you will notice this from the console output. As a quick recap, in this coding exercise, we have seen what a livelock is, as opposed to a deadlock, and how in a livelock situation, multiple threads are continuously retrying to gain access to a shared resource, but all failing. A more practical version of this example is a banking application. Imagine you have two bank accounts and there are two pending transfers between the two accounts in different directions. The first transfer aims to move an amount from account A to account B, while the second transfer aims to move another amount from B to A. In order to perform the move and protect the integrity of the balances, both accounts need to be locked in the same time. However, As neither transfer threads will get both locks at the same time, the application will fail for potentially a long time, if not forever. In this coding example, we have seen a more practical example of a livelock with a banking-related example. The two threads were represented by money transfers, which were failing since neither of them could gain access to both accounts in the same time. The third multi-threading issue that we'll touch on doesn't necessarily result in an application hanging forever, but it does result in performance degradation, and the user having to wait for potentially a long time before an action is executed, due to the system being held by a single thread. This happens, for example, if a single thread holds the lock to a file, not allowing any other application or thread to access that file. This can also happen if the lock is held on the wrong object or at the wrong level, such as on an entire list rather than on an individual object. A real-life example for this situation is a person who is using a shared internet connection, such as the one in your school, university, or office, to download large files via a peer-to-peer application. That person will use a large number of connections and most of the bandwidth, preventing colleagues from browsing the web or receiving emails. To create an example for thread starvation, let's use the previous Java example of a banking application, even with a single transfer. But this time, let's add a balanced monitor thread. This thread is meant to periodically check the balance on an account and ensure it's above zero. In case it drops under zero, it should print an alert to the console. As the balance transfer thread will acquire the lock on the bank account, no other operation can take place on that account, unless the transfer thread acquires the lock in the split second when the monitor thread iterates. This can potentially wait a long time before completion. In this last coding example, we have learned about a new concept, thread starvation. As this is somewhat related to livelocks, it represents the situation when the thread execution is badly managed, so the overall application is taking more time than it needs to in order to complete, or hangs forever.